So, random variable basically means that it is a variable that takes on the outcome from an experiment. So the experiment can be anything. Let's take the experiment of rolling a dice. So when you roll a dice, the possible set of outcomes are 1 comma 2 comma 3 comma 4 comma 5 comma 6. So these are the possibilities of rolling a dice. These are the possible outcomes when we roll a dice. Now, what random variable means is that random variable is just a character, okay? And this random variable will take different numerical values based on the outcome of a random event or experiment. So this is the experiment that we have done, rolling a dice. And this random variable can take any of these values based on the experiment that we do. Let's suppose if you are doing an experiment for the first time, when you roll a dice for the first time and you got the outcome as 2, and that outcome is what will be assigned to this random variable x. Okay, so the random variable will take that output. So when you're rolling the dice for the second time, if you're getting the random variable as 3, I mean the outcome as 3, the random variable will take that outcome. So random variable is nothing but a variable that takes the outcome of an experiment and stores within it. So that is what random variable basically means. So random variable can take different numerical values. What does different numerical values means? Different numerical values are possible uh, when you roll a dice. So those are possible outcomes basically. So different numerical values means different possible outcomes. So these are different possible outcomes when you're rolling a dice. And that outcome is taken by a variable, and we call such variables as random variables. Okay, so this random variable can be of two types. One is discrete random variable and the other one is continuous random variable. Now let's take another example of calculating the heights in a class. Okay, you want to calculate you're doing an experiment of calculating the heights of students in a class. So when you're doing that experiment, you're taking the heights of different students in a class. So when you're doing that stuff, you're getting the outcomes as 5.12, 5.13, 5.135, 5.1356, 5.1366, 5.14, 5.145. So it depends on the number of students. Even if look at this, so if you are rolling a dice 1,000 times, so you cannot get any output beyond these numbers, right? So even if you roll this dice 10,000 times, you will not get outcome beyond these numbers. Even if you're doing this 1 lakh times, it doesn't actually matters. Any number of times that you do, the outcome will always be out of this particular set, right? So but when you're here, you just calculated the heights of 8 students or 7 students. You just calculated the heights of 7 students. But when you calculate the heights of 1,000 students, how does this look like? It will not be a defined set. It will not, that heights of those 1,000 students will never be from this output, right? It automatically changes. It automatically changes, right? It will not be from this set of outcomes. So when you're increasing the students, some of the students height might be 1.53667, okay, or 6678. Some other students will get 5.13655. So the more you do the experiment, I mean the more you collect or the more you do the experiment, the more the values will grow. It will not come from the defined set. That is what I mean to convey here. So when you increase the number of students, this set will also increase. The set of outcomes will never be constant. So we will get an outcome from infinite set of possibilities. Understood? But in the other case, even when you roll the dice, this is one experiment. When you roll the dice even 1 lakh times, 10 lakh times, the outcome will always be from this set. But when you're taking the heights of students from 1 lakh, the 1 lakh students height will not fall in this range. It will keep on growing, right? Some can be 5.66 feet. So when you take 2 lakhs, some of the students can go to 7 feet. Some of the students can fall in 3 feet. You don't know. So the set of outcomes, set of possible outcomes is increasing. The set of I mean, it looks like infinite range, right? The students can fall in any of these numbers, or some new numbers can get added. They will be already in the set. The heights can already be within the set that we have calculated. It means like two students heights can exactly match. So that is what infinite set of possible values means. So when you're getting this outcome from a possible set of values or countable number of distinct values, such kind of random variables are called as discrete random variables. But when you're getting the outcomes from infinite set of values, such kind of random variables are called as continuous random variables. So this is an example, rolling a dice and getting the heights of students. As we keep on increasing the sample, or as we keep on increasing the number of experiments that we do, it is keep on increasing. The possible set of possible outcomes of the student heights are keep on growing. So that is what continuous random variables means, taking on an infinite number of possible values. So when you consider the heights, you are getting infinite number of possible values. But when you're rolling a dice, you are getting finite number of values. So outcome can never go beyond these numbers, 1, 2, 3, 4, 5, 6. Even if you have done that 10 lakh times. But when you take the height of 10 lakh students, definitely the range will keep on growing, because heights will never be constant, or they will go up to decimals. Decimals will also do an impact on the heights. So that is what discrete random variable and continuous random variable difference means. Is that clear now
Yes.
for everyone?
Yes.
Okay.
Yeah.
Um, right. So now go back to understanding a small thing. Okay. So I'm trying to put this in a graph, okay? And then from there we just have to understand something, and then we can go to the next concept. Um, Let me just clear this. Okay. I'll just go back to Paint, and I want to explain something there. Now we are talking about two experiments, right? The first experiment is rolling a dice. The second experiment is calculating the heights of students in a class. I want to just represent that on a graph and see how they actually look like. So this is how there are two experiments now. One is rolling a dice, and the other one is rolling a dice is my first experiment, and the other experiment is calculating the heights of students in a class is my other experiment. Okay. Rolling a dice is my first experiment. The other experiment is heights of students in a class. Heights of students. Heights of students is my second experiment. And now I am doing this experiment from with 10,000 samples. Okay. I am going to do this experiment with experiment 10,000 times, or 10,000 students. In this case, I am rolling the dice 10,000 times. In this case, I am taking the heights of 10,000 students. Okay. So now let's understand this in a graphical way. Okay. So rolling a dice, I'm doing it 10,000 times. What are the possible outcomes of rolling a dice? The first question is that finite set or infinite set?
In
Finite set.
Finite set.
Finite set.
Finite set. And what are the finite values of rolling a dice?
1
1
by
to
1 to
3.
6,
1, 2,
6.
3, 4, 5,
1,
6.
2.
3.
So you will be getting from the finite set, right? 2, 3, 4, 5, and 6. And what if I'm taking the samples of 10,000 students' heights? Will that be a finite set or infinite set?
Infinite set.
Infinite set. And so let's take this example. I'll just take some random values like 5.1 can be height, 5.12 can be height, 5.13 can be height, 5.13, comma 5.135. It actually looks like this, right? 5.13, and at some point it goes to 5.5, and at some point it reaches to 6. At some point it reaches to 6.5. But even if you come back, so this can also looks like this. It can start from 4 feet, 4.1, it goes till 4.6, so on, right? This is how the heights of students will flex. So there are infinite number of possibilities when you're talking about the height of students. But when you're rolling a dice, you always get from an finite set of values. Even if you are doing that for 10,000 times or 10 lakhs times, or it doesn't really matter. But this always remains finite, and this will always grow. It can always be infinite. Now, when I say the probability of getting 2, when I roll a dice 10,000 times, okay, so can you actually predict that? The probability of getting 2 when rolling a dice 10,000 times.
1 by 10,000.
1 by?
10,000.
10,000.
Okay. Now the probability of getting a student's height 5.136 of 10,000 students.
Undefined.
We can't determine.
Can't say.
Yeah, we cannot actually determine. So in that cases, if you are taking the value of the infinite set, the probability will always become 0. But what we can say with the infinite sets is, what is the probability of getting the student's height in between 5 and 5.3? 5 and I mean 5.1 and 5.3. You can say such kind of probability because as this is continuous, if any particular value getting the probability of any particular height will always be 0. We cannot actually as it is an infinite set, the probability of getting a particular height will always be 0. But what we can calculate is what is the probability of students within 5.1 and 5.3 is what we can calculate, and how to calculate and all that stuff we will understand that shortly. So let's come back of representing this in this form. So I'm going back to the slide again. So this let's represent this in the graphical form in a two-dimensional space. So one is a student and the other one is their heights. So this is rolling a dice and the outcome. So here comes the rolling a dice and here comes the outcome. So this is an experiment rolling a dice, and number of times the outcome might have occurred. Number of times outcome happened. So this is a cumulative total. Okay, just understand that. So when you're doing it 1,000 times, how many times you're getting one, how many times you're getting two, how many times you're getting three, how many times you're getting four, how many times you're getting five, how many times you're getting six. I'm just trying to graph that. And here what I'll say is total number of students in that particular range. Total number of students with that height. So if you look at this, every number will, I mean, rolling a dice, what are the possible outcomes? So the possible outcomes here are 1, 2, 3, 4, 5, and 6, right? So what are the possible outcomes here? So the only possible outcomes here are 1, 2, 3, 4, 5, and 6. Okay, so these are the possible outcomes of rolling a dice. But what are the possible heights? This cannot be actually predicted, right? You cannot actually mention that on this label. So because there are infinite number of variables, you cannot say 5.1. Between 5.1 and 5.12, there are infinite number of values. Okay. So you cannot actually represent, we'll just represent the ranges. Like let's suppose I'll say 4 feet and 5 feet and 6 feet. This is how I say. And now if I represent this in a graphical form, how do I do that? What is the probability of getting one in this 1,000 when you roll a dice 10,000 times will have the equal probability. I mean, 2 will have the equal probability, 3 will have the equal probability, 4 will also have the equal probability. What this just means is every number when rolling a dice, every outcome when rolling a dice will have the equal probability, right? Agree? So when I roll a dice 6 times, okay, what is the probability of one?
1/6.
1/6.
What is the probability of getting two?
1/6.
1/6.
What is the probability of three?
1/6.
So
1/6.
every number has equal probability, right? So there is an equal probability of every number when you are rolling a dice. Even if you roll a dice 7 times, what is the probability of getting one? Will be equal to probability of getting two. Whatever the probability keeping that aside, every number will have an equal probability, right?
Yeah.
So the same applies when you roll a dice 10 times, every number will have an equal probability. When you roll a dice 10,000 times, every number will have an equal probability. Is that right?
Mm.
So whatever might be the probability, the probability of every number will always be equal. That's what I'm trying to say over here. So every number will have an equal probability. Whatever the probability depends on the experiments that we do, but every number will have an equal probability all the times. So that is what it means. But if you look at this case, um, so let's calculate the probability of getting 4.1 is, I mean, it just says total number of students. Like let's suppose if you're doing this, the total number of students falling within four, I mean, let's suppose I have 4 to 4.1. I'm dividing this into bins. So let's say I get 10 students in this range. Okay. And beyond that, if I'm getting from 4.1 to 4.2, I got somewhere around uh, 16 students within that, falling within that range. And because any height, the probability would always be zero, the possibility would always be zero. We cannot actually say that particular height will have a possibility. I mean, any student will have that particular height, but within that range we can say. So next goes some range. So next goes some range. I mean, some students may fall in this range, some students may fall in this range. I mean, these number of students might fall in this range. If you take the number of students between 5 to 5.1, so let's suppose 100 students have 100 students are there in that range. So I'm representing like 100 students within that range. So this can all, if I draw a graph about this will always be continuous. So this will always be continuous. Right? So I'm just, if you make the bins very smaller, that looks like this. So I'm making the bins little much smaller. Okay. So what I'm actually trying to convey here is that so when we have infinite values, you cannot predict the probability of any one value. So the probability of any value will always be zero. But what you can actually calculate is the number of students falling within that range, or the probability of students heights falling within that range is something which can be calculated. So because we have infinite number of outcomes, here we have possible number of outcomes, so you can always predict the probability of getting a particular outcome. But here it is impossible, so you always have to go with ranges when you have infinite values, or when you're dealing with continuous random variable, capital X. So if you look at this, I can subdivide. I mean, if I make the bin sizes little smaller, you can actually look at this continuous graph, whether it is whatever it is. Like if I draw another square here, I don't know why it's coming as white. Okay. So if I draw another small bins here, what actually happens? It looks similar to this, right? So when you make it little smaller, the graph looks similar to this. You just have to make the bins much smaller. I mean, when you make the ranges much smaller, you will actually get to know about that. Something of that sort. As the bin sizes are more large, you don't see the graph is exactly touching the tips. But when you make the bins little smaller, you will see a continuous graph. So that is what actually X means. I mean, how the continuous random variable looks like, the values of continuous random variable. So I'll go back to the slide, and I'll just walk you through the next stuff that we are talking about. So we are clear till this point, right? Like a continuous random variable and discrete random variable. Continuous random variable will always take values from an defined set of values. So it will always take from defined set. Okay. So if you look at this, um, you understood what is a random variable, and you also understood what is discrete random variable and what is continuous random variable, and the representation of that, how does that actually look like. So what this says, continuous random variable takes on an infinite number of possible values from possible values within a given range. So the exact height of students in a class, possible values, any real number within a range. Okay. So now that is what random variable means. So it actually takes values from infinite set of possibilities. So now going back to probability distribution. So each random variable has an associated probability distribution, which describe how the values of the random variables are distributed. So how the values of random variables are distributed. We will come back to this line. But for discrete random variables, probability distribution of each outcome is represented by probability mass function. So the probability distribution of a discrete random variable is represented by probability mass function, which gives the probability that the random variable takes a specific value. So random variable taking a specific value. If x is the outcome of a die roll, probability of getting x is equal to 1, probability of getting x is equal to 2, x equal to 3, and as I said, the probability of every outcome when rolling a dice is same, and that will be equal to 1 by 6, because there are 6 possible outcomes, and we have just we are talking about the probability of getting a particular outcome, which will always be 1 times, which is always 1 by 6. So we represent this probability distribution on a graph. The probability of each outcome is represented by probability mass function. So probability distribution basically means it represents the probability of each outcome. It doesn't represent the value, it represents the probability of each outcome. And that is called as PMF, probability mass function. Probability distribution is nothing but it calculates it represents the probability of an outcome. Random variable will just store the outcomes, whereas probability mass function or probability distribution, in the case of discrete random variables, probability distribution itself is called as probability mass function, which calculates the probability of that random variable taking a specific value, gives the probability that a random variable taking a specific value. So if it gives the probability of the random variable taking a specific value means it is the probability of random variable, which is x, taking on 1, which is the outcome of which is the outcome. So the random variable can take 1, random variable can take 2, 3, 4, 5, and 6. Because we are rolling a dice, only these are the possible outcomes, and the random variable can take any of these values. And what probability distribution mentions is that what is the probability of the random variable taking on a specific outcome or specific value. So that is what probability distribution basically says. It says it also describes probability description also describes how the values of the random variables are distributed. Okay, so it's like probability distribution. So as I said, let's take the example of a dice. I'll try to keep this little easy. So what probability distribution says? Probability distribution basically represents the probability of a random variable taking a specific value. What is a random variable? It is a variable that takes the values from the outcomes of an experiment. Okay, takes on different numerical values from the outcome of an experiment. So rolling a dice is the experiment now. Okay, rolling a dice is the experiment, and the outcomes that are possible with that experiment are 1, 2, 3, 4, 5, and 6. So what random variable can take? Random variable can take any of these values 1, 2, 3, 4, 5, 6, because random variable takes different numerical values based on the outcome of a random experiment. So random variable can take 1, random variable can take 2, random variable can take 3 or 5, 6, 4. The reason being it takes different numerical values based on the outcome. Outcome is the sample space of an experiment, right? All possible outcomes is the sample space. So these are all interrelated. So X takes any value from the sample space, from in this case 1, 2, 3, 4, 5, 6. What probability distribution basically describes is the distribution of probabilities. We calculate the probabilities of random variable. Random variable taking a specific value. Specific value in the sense outcomes of an experiment. What is the probability of x taking 1? Probability of random variable x taking 2. That is what probability mass function basically calculates. The probability of each function is represented by probability mass function. The probability of each outcome is represented by probability mass function, which gives the probability that the random variable takes a specific value. Random variable takes a specific value. Okay. And this describes the distribution of those random variables, describes how the values of the random variables are distributed. Describes how the values of the random variables are distributed, the probabilities of the random variable. So the probability of random variable x is equal to 1 is 1 by 6. The probability of random variable x taking 2 is 1 by 6, because every value when rolling a dice will have equal probability. So if you look at this diagram, just ahead that. So look at this probability mass function for rolling a dice will always have equal probabilities. So 1, 2, 3, 4, 5, 6, these are the possible outcomes. Whatever is the how many experiments that we do, always they will always have equal probabilities. So that is what this graph basically specifies. Okay. So, but for continuous random variables, is this clear? What is probability distribution? Probability distribution is associated with random variables. Each random variable has an associated probability distribution, which describes how the random variables, how the values of the random variables are distributed. So this basically, this is a graph which describes the distribution of random variable, the probability distribution of a random variable. Is this confusing or clear
Clear.
for everyone? I'm not sure.
Yes.
These are very important when we derive. Right after this session, we are going to start with understanding the machine learning concepts. So I think probability distribution is the major important thing that helps us to derive various things in machine learning. So probability distribution, until the previous slide is just for your understanding, to understand what is experiment, what is an outcome, what is an event. But this is most important thing. Understanding a random variable and understanding probability distribution of those random variables. I'll just repeating it again. Understand this by this definition. Each random variable has an associated probability distribution. What is probability distribution? Probability distribution of each outcome is represented by the probability of each outcome is represented by probability mass function, which gives the probability that the random variables take a specific value. So random variable taking a specific value is called as probability mass function. And the probability distribution describes how the values of the random variables are distributed. So it actually represents all the possible outcomes distribution. That is what probability distribution is. So that is what this graphs actually describes. So these are the outcomes and these are the probabilities of different outcomes of that particular experiment, and how those are distributed is what this is saying. So what is the value of 1 by 6? That is 0.16, right? 0.166 you're getting. So the probability of each value is coming as, each outcome is coming as 1 by 6. So the probability of every value when rolling a dice will become 1 by 6. So that is what this graph is actually representing. This is called as probability distribution of different random variables. And when you take the continuous random variables, when you're talking about the continuous random variables, you cannot actually specify each values, because as you have infinite number of values, the probability of getting any value is always 0. So just look at this probability distribution. the probability of continuous random variable taking any specific value is zero. Because as there are infinite number of possibilities, probability of getting any value in a continuous random variable is always zero. So instead of probability mass function, what it actually happens, it calculates the probability of getting a specific value, specific random variable. Okay, a specific value for a random variable is what probability mass function calculates. That's what we have seen in the previous slide. Probability mass function is always related to an individual outcome or the probability of a particular numerical value as an outcome. So that is what discrete basically. These are internal discrete. Each outcome probability mass function always takes. There will be a probability of getting a specific outcome because we have defined set. When coming to the infinite values or continuous random variables, probability of taking any value is always zero. You cannot actually say there will be a probability, but it can be described with probability density function. Density itself says how many people falling within that range. What basically density means? Density is nothing but the concentration. Concentration means how many people are falling within that range. So let's suppose if you are taking a specific area and you have so n number of people over here, like some people are living over here, let's suppose. So what does this density means? Like this is one area that we do have, and this is another area that we do have. Okay. So looking at this diagram, what do you say? Let's suppose they both have equal area. Both of those places has equal amount of area. But if you look at these diagrams, uh, can you say the density of the people in this region is higher than this? Density basically specifies, the word itself says how dense the people are living over there. I mean, how many people are living for each square meter or each square kilometer. That specifies the density. Let's suppose this is 1,000 square kilometers area, and this is 1,000 square kilometers area, and this is a block of 100 square kilometers. Okay. So these are 100 square kilometers. So in 100 square kilometers, here you just have two people living. But here in 100 square kilometers, you have around 10 people living. So look at the density. So density space says what is the concentration of a particular people in that particular area. That is what density example says. So when you have highly dense area, more people will be living in small area. When you have less dense population, that means like very minimal people will live in that particular same area, like 100 square kilometers or whatever it is. So have you understood that density? That probability density function is basically the probability of people or probability of a particular random variable taking a specific value, like probably, I mean, range of values. To consider a continuous random variable x that is uniformly distributed between 0 and 1. So the probability of random variable x in between 0.2 and 0.5 is what probability density function means. Probability density function always calculates the probability in a range, not for a single value. Here we are calculating the probability for a single value, but here we will calculate the probability of people living within that range. It can be 160 to 165. We are going to calculate the probability of that particular height range. So here we will draft what is the probability of students students height will be in between 160 and 165. That is what probability density function means. Probability mass function will always deal with single values. Probability density function will always deals with range of values. Look at this. The probability of random variable x taking the value in between 0.2 and 0.5. That is what probability density function means. Why we are calculating probability density? Because you have infinite set of values. So when you have infinite set of values, taking the probability of getting any single values is always zero. So you cannot actually tell that. But what you can say what is the probability of people or heights of students falling within 160 and 65. That is what probability density function says. So if you so look at the background diagram, which are in green colors. So this says I have the probability of 0.004 or something of people height in between 145 and 150. So I have the probability of 0.1 for the people living in, I mean, where the people's height is between 150 and 155 centimeters. The probability of students' height within 155 to 160 is 0.15. Similarly, 160 to 175 is 0.27 or something, somewhere here, right? Somewhere here. I think it is 0.25. So what is the probability of students between 165 to 170? So in continuous random variables, we always calculate the probability of a random variable falling within that range. Whereas in probability mass function, we always calculate the probability of a specific value. That's why it's giving like probability of random variable taking a specific value, because we have defined outcomes. So that is called as probability mass function. Whereas when you have continuous values, you always calculate the probability of values getting in between 0.x and probability of random variable taking the value within a range. So that range is what we are going to calculate. And when you calculate all that stuff, as this is continuous, you will just draw a line to represent that particular graph. As this is continuous, the graph also has to be continuous. And this helps us to predict any kind of value within that. So now when you derive this graph, when you have drawn this graph, if you want to calculate the probability of, you know, getting a specific value, you have to calculate the area under that curve. That is what specifies the probability of getting a value um, under that. So now you don't have this, you have calculated this based on the results that you do have. But when you want to calculate, now it is given that 160 to 165 is what you have calculated, but I want to calculate the probability of random variable x getting in between 162 and 165, like 162 random variable taking the value between 162 and 165. So this is 162 and this is 165, right? Now if I want to know this value, what I have to do is I have to calculate the area under this curve, under this space. So if I'm able to calculate the value under this in this range, I have to calculate the area under this curve. I'll get the probability density function, or the probability of a random variable taking a value in between 162 and 163. Okay, so to do that, what you have is you have this probability density function f of x. So this f of x basically represents this graph. So if this is a single line, it will be represented by f of x as 1. Okay, so this is random variable and this is the graph that represents a random variable. Similarly, this will have a function which we will know later. And now what you have to do is you have to calculate the area under that curve. So how do we calculate the area under a particular curve? You have to do an integration. When you do the integration basically gives the area under the curve. So when you want to get the probability of a value between 0.2 and 0.5, you have to integrate the probability distribution function from 0.2 to 0.5, and when you calculate that value, you will get that probability. That is what probability density function basically will do. It gives us the graph, and using that graph, we can get the probability of a random variable taken any kind of values. Or you want me to repeat this again? So you have to understand integration will always gives us the area under the function. So whenever you do an integration, it always gives you the value under that particular curve. So f of x for in uniform distributed, this is uniform distribution curve. How a uniform distribution curve looks like. It looks like a single line. So this is represented by 1. And now when you replace f of x with 1, the integration of 1 d of x is x. So you have to apply, this is x, integration of dx is x, and you have to apply this range as 0.5 to 0.2. So you replace x with 0.5 minus 0.2, which is lower bound. And when you calculate the difference, which is 0.2. So the probability of x taking 0.2 to 0.3. So this is 0 and this is 1, 0.2 to 0.5. So the area under this curve is given by this integration, and the probability of random variable taking 0.2 to 0.5 is 0.3. That is how the probability of continuous random variable is calculated. So you have come across few things. One is random variable. You have understood what is discrete random variable and what is continuous random variable. And you have understood what is probability mass function. Probability mass function is nothing but it specifies the distribution of random variable taking the probability of a random variable taking a specific value. What is the probability density function describes? Probability density function always describes the probability of a random variable taking within a range of values. Probability of random variable taking within a particular bound, which is 0.2 to 0.5 or 0.5 to 0.7, whatever it is. So that is what probability density function specifies. Using the probability density function, you can calculate the probability of a random variable taking a particular value. You just have to calculate the area under the area between lower bound to lower upper bound for that probability density function. So probability density function actually describes this curve. And when you integrate this curve, you get the area under this curve. So from where to where you have to integrate, it depends on from where to where you want to find out the probability of a random variable. So if you want to find the probability from 162 to 172, so the lower bound will become 162 and the upper bound will become 172. And you have to take the f of x. F of x is basically the function which represents this curve. Yeah, so in simple case, this is one of the curves that we do have, and it is represented by 1 because this is y-axis, which is 1. Uh, so this will be represented by 1. Uniform distribution will always be represented by 1. And if you take this f of x and if you integrate this, so based on this function, you have to perform the integration. So I can just show you different types of distributions. So you'll get some instant. I can repeat this if you don't understand this. I think it is going little complex. Different types of distributions with equations. So these are different types of distributions. So this is uniform distribution. Okay, this is exponential distribution, and this is normal distribution, and this is binomial distribution. These are all discrete distributions. Okay, geometric distribution, hypergeometric distribution. Look at the probability. How do we get this probability p of x less than or equal to x? We have integrated from a to b, and you have given that function. So this is a step function basically, but this is uniform from a to b. This is a step function. Can someone say the equation of this function? What will be the equation of this function? Have you heard about anything like deriving the equation for a particular graph? X2 minus x1 is equal, let's suppose I'll take a simple graph here for you to explain. If I take this paint again, so can you say the equation for this? Equation for this line?
X is equal to
This is x and this is y.
f of x is 1.
You heard about this mx plus c for lines.
X
C is intercept, x is this x-axis and y is y-axis, the different axes that we do. And this
X
is
is equal to Y.
so this is x is equal to y.
Y.
Slope of this is when the slope of this is 1, it becomes y, x is equal to y. And the slope of this is equal to 2, it becomes y is equal to 2x. And if it is not passing through the origin and if it is passing through some other stuff, you say that y is equal to 2x plus there will be some intercept 3. How do we actually calculate this? Let me show you that. So when you get to understand that, you will be able to derive or find out the area under a particular curve. So how does integration actually helps us to find out the area under the curve is what we have to understand. So we can come back and revisit the probability density function as again if you don't understand, but it is important to understand. But let's understand how to actually calculate the area under a curve. Let's suppose I have this square, okay, and I'll say this 0 1 and 0 1. What is the area under this curve? I mean, if you calculate this, is this looking like a square?
Yes, the area is 1.
The area is equal to 1. Now if you want to integrate this, how to do that? So you are integrating the from 0 to 1. What actually describes this? So this is just here x is equal to 0, right? This is a straight line. What is the equation of a straight line?
X. X. X.
So equation of a straight line is always y is equal to mx plus c. That is we have talked about, right? Standard form of any line is ax plus by is equal to c. Slope intercept is y equal to mx plus c. Point slope from y equal to. So I think you have to I mean learn deriving the equations. Um, there will be 2-point form, which is x2 minus x1 is equal to y2 minus 1. So 2-point straight lines. So when you have 2 points, how to actually get the equation of that straight line is something that you're trying to understand here. So this is the formula. Where is that? y2 minus y1, y minus y1 by x minus x1 is equal to y2 minus y1 by x2 minus x1. So this is basically the calculation. So if you take, I have 2 points here and I want to calculate the equation of that particular line and then I can integrate that equation. So if I go back there, I'll just cut this and paste it there. So y minus y1, y2 minus y1. So I'm taking this and going back to the paint and pasting it there. So now I'm pasting it here, right? So now this is the equation that I do have. Now I have 2 points. What is this point? Tell me what is this point? Yesterday we have seen, right? These are the 2 points that we do have. We want this equation.
1,
1,
1,
1,
1,
What is this point?
0, 1.
0, 1. Now
0, 1.
so this is x1, y1. This is x2, y2. Now we just have to apply in this equation, that is y minus, what is y1? 1 is equal to y2 is 1, y1 is 1 by, sorry, y1 is also 1, right? So this becomes
1.
1 minus 1. So I'm going back here, 1 minus 1 and x2 is 1 minus x1 is 0.
0.
X minus, what is x?
0.
1 is 0. So the equation becomes y minus 1 is equal to 0.
1.
Something will always be 0. So y is equal to 1 is the equation of this particular line. Okay. So now I have to integrate this. So this becomes y into dy. I'm doing this along y-axis. So this is the integration. Now you know what is the integral of y into y. No, sorry. This is f of y. F of y is just 1 here. So y is equal to 1. So you have to integrate. So this is actually 1. So 1 into dy. So this becomes y 1 to 0. So that becomes 1 minus 0, which is equal to 1. So the area under the curve is equal to 1. Understood?
Yeah,
Okay.
understood.
Similarly, now what we are trying to do, we are trying to, if this graph lies here, somewhere like this is square. What is the equation for that? How does, like, you can represent these points 1 comma 2 and this is 1. So this can be written in such a way that f of x is equal to 0 from 0 x less than 1, and f of x is equal to, what is this? 1. So this is x and this is f of x, let's say. So f of x is equal to 1 here. So f of x is 1 from 1 less than x less than 2. Right? And f of x is equal to 0 beyond that. And what is this? F of x is equal to, again, 0 when x is greater than 2. Now when you want to find out the area under this, you have to say f of x into dx. So f of x, from where there is a value from 1 to 2 only, right? So from 1 to 2, 1 into dx. So that is x, which is 2 into 1. So this becomes 2 minus 1, which is equal to 1. Okay. So now if you calculate the area under this curve, this is also 1 into 1, which is equal to 1. So this is another way of doing it. Vertical form and horizontal form. So if you take this as an f of x, so this is how it actually looks like. So basically what you have to understand is, if you do an integration for a particular function, you are getting the area under that particular range. So when you want to find out the area from 1 to 2, what you are doing, you are just trying to integrate this f of x within that bound. So if you go back to the slide, it is saying the same. When you are trying to find out, so you know that probability of getting a value between 0.2 and 0.5 will be given by the area under that curve, right? So you are always getting that area under the curve. So you know, when you want to find out the probability of a random variable taking from 0.2 to 0.5, that will be given by the integration of the function. F of x is nothing but the graph which is given over here will be represented by f of x. So this is f of x. So when you know f of x, and you just have to integrate that f of x from 0.2 to 0.5, and you will get that particular value. So you just have to know how to find out this f of x. So we will have some standard distributions already given. I mean, we have some standard formulas for different distributions. So distribution is nothing but, this is the distribution. Distribution is how the random variable got distributed. How the probabilities of a random variable picking a particular outcome is distributed is what describes the distribution or probability distribution of a particular function. So there are specific formulas for f of x. What you have to just do is when you want to find out the probability within a particular range, you just have to integrate that. That is only the takeaway. Okay. So for discrete values, it's straightforward, but for continuous values, you cannot, the probability of a random variable taking a particular value will always be zero. But you can calculate the probability of a random variable taking within a range. When you want to find out that probability, you always have to do the integration of that particular probability function. And from where to where you have to integrate, depending on from where to where you have to find out the probability of a random variable taking a particular value. So this says the probability of random variable taking a value within this range 0.2 to 0.5. The probability of a function taking a value from 160 centimeters to 162 centimeters. So that becomes 160 to 162. And what is f of x? F of x is the function which represents this particular graph. So that becomes f of x into dx. So you have to integrate this and you have to apply this lower bound and upper bound, and then that gives you the value of the probability of random variable taking that particular value. So that is what probability density function is. Probability density function is continuous. Probability mass function is discrete. Probability density function will always be used for continuous random variables. Probability mass function will always be used for discrete random variables, where the outcomes are defined. And in continuous random variables and probability density functions, the range of values or range of continuous random variables the random variable will take values from infinite set of possibilities. So have you got some understanding on this, or you haven't got anything? Leave about how to calculate these functions for now. In most of the cases, we have to memorize based on the distribution. So this is called as normal distribution, and the function for there will be a standard function for this f of x. So f of x will be represented by will be given by a standard function, something like 1 by the root of 2 pi into sigma. You will get to know e to the power of minus x minus mu whole square by the 2 into sigma. So there will be a constant function that represents every normal distribution. In the most of the experiments that we do will have the normal distribution itself. So we already talked about normal distribution in yesterday's session, right? So what actually we already have taken examples of students in a class and how the heights of the students in a class are distributed, and that resembles normal distribution is what we have talked about. And we also know what is mean of this normal distribution, what is the standard deviation of this normal distribution, and where most of the students heights will concentrated. We already talked about normal distribution. We are going to talk about this in detail, and we are also going to learn about these probability distribution functions of normal distribution. But keeping all that aside, you just have to understand you just don't have to bother about this f of x, how to get the f of x for a particular distribution. You don't really need to bother about this. There will be constant functions. You just have to memorize based on the distributions. Most probably we'll always work with any set of data uh, will falls under around 6 kinds of distributions, not more than that. But most of the data sets will fall under normal distributions. And there is also different theorems like central limit theorem, which says that actually says a different thing. And then you will understand what is the predominance of normal distribution. You will learn all of them later. So the distributions and all. But for now, you have to understand what is probability density function actually means. I just want to make sure we are very clear with this going forward. So with my interest, I just want to repeat everything that we have discussed so far. But as you have got some understanding by this point, you try to concentrate more better as I repeat this again, so you'll get a better understanding. So now coming back to the random variables again, is that okay if I repeat this, or you got a clear understanding by now? Hello?
Yes, man, got an idea, but we need to revise once to get better idea.
Yeah, I'm just repeating it again. Maybe with questions, I'll just repeat this. Now, what is random variable? What you got out of what is your understanding on random variable? What is random variable?
A variable which stores value of an outcome.
Yeah. So a variable that can take different values of based on the outcome. So it can take any value from the outcomes that are possible. That is what random variable is. It actually, in the first case, it can take two. In the second case, it can three. It's just a variable that takes the outcomes. That's all. That is what random variable is. So we have seen the experiment of dice, and the possible outcomes are 1, 2, 3, 4, 5, 6. So in that case, the random variable will can take only the value within that set. It cannot take 7 because 7 is not part of the possible outcomes of that experiment. So random variable will always take the value or from the outcomes that are possible. Okay. So that is what random variable is. Just treat it as a variable which takes different values. And what are those different values? Different values are one of the outcomes of an experiment. Okay. So for example, if you take the dice, the possible outcomes are 1, 2, 3, 4, 5, 6. So this random variable takes one of these outcomes. It can take any of these outcomes technically. So that is what random variable. What are the types of random variables? There are two types of random variables. The first type is discrete random variable and the other one is continuous random variable. Discrete random variable means it takes the value from defined outcomes of an experiment. So the outcomes of an experiment are defined, they are not infinite. So they can, if you toss a coin, it can be just tail and head. It cannot be anything other than that. When you roll a dice, it can be just from 1 to 6. It cannot take 7, 8 because they are not possible with that dice. So when you have such kind of defined outcomes, and when the random variable is taking such kind of outcomes, such kind of random variables are called as discrete random variables. When you talk about continuous random variables, continuous random variable can take infinite number of possible outcomes. So when you do an experiment, there are infinite possible values that the experiment can produce or outcomes that the experiment can produce. So when you take the heights of the students, it can produce infinite number of outcomes because they can go to decimals and the values looks like infinite values. So when the random variable is taking the values from the from the outcomes of such an experiment, we call that as continuous random variable. Are we clear till this point? Hello.
Yes.
Now let me ask question one after the other. So let's suppose if I take the temperatures of a room, will that fall under
Yes.
continuous random variable or discrete random variable?
Continuous random variable.
Continuous.
Continuous, right? So if I heartbeat of a person in a day,
Continuous.
Continuous.
So in a day,
Dis, dis,
capital and continuous.
Yes.
continuous, right? So what are standard expressions?
Evidence.
Tossing a coin.
Discrete.
Discrete.
Okay, let's just see more examples to understand this. Real world examples. So number of heads in coin flips, number of defective items. So we talked about number of heads. We talked about, we talked about rolling a dice. Look at this example, number of defective items. So in a batch of 50 widgets, the number of defective widgets in a discrete random is a discrete random variable. So what are the possibilities of defective widgets in a batch of 50? It can be just 1 to 50, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. So it always can take only within that 50. It cannot take 51, right? So it becomes discrete random variable. Agreed?
Yeah.
Yeah.
Yeah. Such kind of examples. Now let's see the examples of.
Continuous.
So heights of individuals we have discussed. Time to complete a task. Running a marathon or baking the cake. Temperatures we discussed. Weight of objects, weight of fruit, vegetables, or any object can be measured to a degree of accuracy, making it continuous random variable. Amount of rainfall is a continuous random variable. Time to complete a task. So we already discussed this, right? This is normal distribution. Most of the students will fall within this range. We again are going to discuss this. You also understand mu. What mu is the mean, sigma is standard deviation. You know what is mean and what is standard deviation. Leaving all that apart, you're just trying to understand examples of continuous random variable. Heights of individuals can be continuous. Time to complete a task. So one can take 2 minutes, one can take 2 minutes, 2 seconds, 2 minutes, 5 seconds, 2 minutes, 10 seconds, 2 minutes, 10 seconds, 5 milliseconds. So that is continuous. Temperatures can be continuous, 23.1 degrees Celsius, 23.2 degrees Celsius. So these are simple examples of discrete and continuous random variables. So are we clear till here?
Yeah.
Okay. Now you have to understand probability distribution. Probability of a random variable taking a specific value and their distribution in simple words. So now you know what is random variable and what are the values that the random variable can take. But now you're calculating the probability of a random variable taking a specific value from the outcome. Okay. Now you know probability x can take just 2, right? The probability of x taking x2 would be 1 by 6. Now, in probability distribution functions, you're calculating the probability of a random variable, picking a specific value from the outcome, and studying and drafting the distribution of that random variable, taking that particular probability is called as probability distribution. Okay. So what you're doing here, when it is discrete, when you say discrete, the outcome should be from a specific set of values. So when you're calculating the probabilities, the first step to draw a probability distribution function or to derive a probability distribution function is calculating the probability of the outcomes in the discrete case. So when you calculate the probability of the outcomes, what is the probability of x, a random variable, taking the outcome 1? So the random variable picking the value 1 has the equal probability of picking value 2, has the equal probability of picking value 3, 4, 5, 6. Every outcome here will have equal probability, right? Which is 1 by 6 because out of 6, there is one chance. So you calculated the probabilities and represented on a graph which shows you the distribution of the random variable picking a particular value. So that is called as probability distribution. The probability of each outcome is represented by probability mass function. So this is probability mass function, which gives the probability that the random variable takes a specific value. Okay. Probability distribution describes probability distribution. Basically, what it will do, it will describe how the values of the random variables are distributed. Okay. So that graph depicts how the how the distribution of random variables are distributed. It's equal. Whereas coming to the continuous random variables, in continuous random variables, probability of random variable picking any single value or any specific value is always zero. Okay, because you have infinite number of possibilities. Out of those infinite number of possibilities, for a finite number of experiments, it is always zero. The probability will always zero, right? So I already have shown you the example of 10,000 students. If you take the heights of 10,000 students, and if you're trying to calculate the probability of a specific value, it is always zero. Okay, in the worst case it is always zero. In the best cases it may match, but in the worst cases, in the real world, it is always zero. It is better to treat that as zero. It is not possible. Out of those infinite numbers, getting a single value is always zero. So for continuous values, what we do is we calculate the area under the curve. What is that curve? The curve specifies, this curve basically specifies the distribution of random variable taking the specific value from the outputs. Okay. And when you are drawing continuous random variables, you derive that continuous random variable. I mean, you derive that probability distribution by calculating the probabilities within the range. Okay. So you're doing bins, you're creating bins, and then you're calculating the students falling within that bin. You actually, there is a different concept here. So how do you get this graph? How do you understand this? So are we calculating every student falling within that range? Not really. So when you say 10,000 students, let's suppose I have 1 lakh students. Am I taking the heights of every student and I'm going to every student and am I calculating the number of students falling within this range 160 to 162? Am I doing that? Am I going to every student? Okay, the first student height is not 16 point, is not falling within this 160 or 162. Am I going to second student and doing and getting a value between and I'm going to second student, I'm checking the value, the student is falling within this range, I'm incrementing the count. Going to third student, going to fourth student, and I'm incrementing this value to 5 6, and I'm going to 1 lakh student. Am I going to every student? It's not at all possible. But then how I'm getting this graph, how I'm getting this is just an approximation. So in none of the experiments that we do in real world, we never do with all the students. We take the sample out of them to determine how to determine the entire population, or to bring the statistics of the entire population. You always will get the sample out of that, and then you will actually derive these graphs, and from then you will actually describe the population. Okay, so let's understand this in a better way with the different terminologies that we have got now. So when I say population means taking every student within these 1 lakh students. So these 1 lakh students is called as population. Those are the students that we are trying to study the heights of. So we are trying to study the heights of the people of these 1 lakh students. Now, if I take the sample out of these students, I'll just take, whenever I want to study about the population, I will just study about the sample out of that population. Sample means taking some people out of them, or taking some students out of that. You have different sampling techniques. Let's not bother about that. So you take a sample out of it. Sample means I'm taking 1,000 students or 100 students out of this. I'm just taking 100 students out of this. That is a decent sample. Oh, you heard about the election results, right? So when they do results, when they publish post-poll results, what they do, they will not go to every voter and they will ask their opinion. And even they will not say the right candidate that they have voted for. What they will do, they'll just collect some trusted samples. How they collect the samples? They will collect the responses of old people. They'll collect the responses of poor people. They'll collect the responses of rich people, and they also collect the responses from you know the middle-aged people. So they'll just take the sample. They will not reach to every voter and collect those results. They will collect the sample. I mean, if we have 100 voters in a village, they will reach out to 5 to 6 voters, and based on their response they will derive the result. So that is what sampling means. So that 6 samples that they have collected, the 6 responses of the voters that they have gathered, will help them to analyze the a trend of all the 100 voters. Okay, so that is how the analysis happens. So now out of these 1 lakh students, I have taken 100 samples, and using these 100 samples, I'm going to predict these 1 lakh student heights. Okay, now I use these 100 students heights to derive this graph. So this graph is derived by analyzing only these 100 students. By going through this 100 students, it is not so tough to derive this graph. So out of these 100 students, I'll say 160 to 160 students, there were like 15 students. 165 to 170, I have 20 students. And 170 to 180, I have like 30 students. So based on that, I'm just drawing this green color stuff. And once this green color stuff is done, as this is continuous, I'm drawing a graph over the peaks. Once the graph is derived, the continuous graph is derived, now I'll use this graph to derive the heights of, or to know the heights of these 1 lakh students. Now, if someone asks me, now I derived this graph from the sample. Now, someone asked me, hey, you tell me the probability of the students between 160 and 170 centimeters out of these 1 lakh students. Now, what I'll do, I'll just integrate 160 to 170, and I know this function which I derived from the sample, f of x and dx. If I integrate this, the value that is coming out of this is talking about this population. Okay, that is how you derive the graphs, and that graphs will be used to to explain the population. What is this graph? This graph is the probability distribution function, f of x. F of x specifies how the distribution, the possibility of random variable taking, the probability of a random variable taking a specific value from the outcome is distributed, is what probability distribution function means. Understood? So to derive this graph, if you're considering the entire population, there is no point of actually drawing a graph, doing the integrations and all the stuff. So you have the right values. You know how many people are between these heights. You know the height of every people. You just have to filter, that's all. But it is not possible. You have some millions and billions of population that you have to analysis. You have to, when you do such kind of analysis, you have to only take the samples. You cannot go to every voter and ask their response, right? You have to again take the samples and predict the results. They can be right, they can be wrong. It depends on the way you have analyzed, the way you have taken the samples. That is how it works. It is not always true that you will always get the right results based on the way you do the samples. You have seen the recent poll results, right? Not all the polls have given the right results. Only few polls got succeeded. It depends on the methodology. It depends on the analysis that they have done. And I have also told you about training a model and the performance, and analyzing the performance of the model. You will know all that stuff, whether you have taken the right sampling or not, whether your analysis is giving right results or not, again can be analyzed. Okay, whether you have derived this function from this sample f of x, if this f of x is giving right results or not, you can determine that. If not, you can even improve the samples, you can take right samples, or you can do that stuff. But right now you just have to understand what is probability density function. what is random variable, what is probability distribution, what is probability mass function. So this is what we are trying to understand. And once the probability distribution function is derived, this f of x is derived, how you are calculating the probability of a random variable taking a specific value within a range that studies the population. Is this little better than earlier?
Yeah. Understood.
Yes, Mohan.
Yes.
Now, just I'll open the stage for you. What I want is, let's not go forward without actually getting this clarified, because this is really, really very important. So what I want to do right now is, we just spent 2 hours. Okay. Now what I want from you is that any one of you can actually answer this. But what I want is, I want you to explain what is random variable and what are different types of random variables. What is probability mass function? What is probability distribution function? And what is probability distribution? Okay. When you say function is f of x. Remember, whenever you say function is f of x. Function is f of x. But when you say probability distribution, the representation, I mean, how the random variables got distributed. So basically, the function itself is the distribution. Okay, because that function represents a graph that represents how the random variables got distributed. Okay, for discrete variables, the probability distribution is called as probability mass function, and the probability density function is called as for continuous random variables. Those functions will describe the probability distribution of the random variable. Okay, so those functions represents how the random variables are distributed for different outcomes. Describes how the values of the random variables are distributed. Now, before going to anyone, I would like to request Bujumai, can you just bring up your thoughts on these random variables? Maybe you might be having some knowledge on this. Uh,
Okay, Mohan. So random variable, right? It's just the variable where, right, in which we can store the output of a result of what is that? A probability. So outcome. Okay. And the probability mass function, right? And the probability distribution function, both are used to describe the probability distributions only. But they differ in the type of random variable that we are describing. Okay. PMF, right? Probability mass function is used to describe the discrete variables. Discrete random variables. And probability distribute function, right? It uses to distribute the continuous continuous random variables. But both are used to describe the probability distribution only. But the type of variables we are considering, it differs. PMF discrete variables, PDF for
and
continuous variables.
it's as simple as that. So it's a better way of representing probability mass function, probability distribution function are same. They both are used to represent the probability distribution. Probability distribution of what? Probability distribution of random variable taking a particular value of the taking a particular outcome. Outcome can be discrete or continuous. If it is discrete, we call that probability distribution as probability mass function. If that is continuous, we call that as probability density function. So you also know probability density function is f of x. Okay, f of x can be derived from the samples of the by sampling the population. And once the probability density function is derived from this population, you can analyze the population by just integrating within the range that you want to actually know about the population. So whether it can be ages, if you want to study about the people beyond age 80, you're just going to integrate from 80 to to infinity, or 100, whatever it is. If you want to study from the ages from 40 to 50, you will just integrate that probability density function from 40 to 50, right? So that is what all that is all about probability density function. And now I'll give this to if someone would like to revisit and explain this, they can. It's open for everyone now. I'd like to hear from everyone what you have understood from this. Anyone else like to talk about this? Hello. No one? Ashwant? Sai?
Yeah, ma'am. So you want me to go over again on the same
Yeah.
thing?
Just what you have understood, you can just tell that so that it would be just like a revision for everyone.
Oh. So random variable, it is a variable which takes values of experiments, like the outcomes of the experiments. So the random variables, we have two types, discrete and continuous. So discrete, for the discrete random variables, there would be set of possible outcomes. Only those can be possible for that. Where if we come to continuous random variable, then there might be infinite outcomes. Suppose like weight of students in a class. So there might be infinite outcomes, right? So it is called as continuous random variable. Coming to probability distribution, if we calculate it for discrete random variable, we use something called a probability mass function, which is calculated when we take probability of each possible value for a discrete random variable. Whereas if we consider for continuous random variable, we consider another function called as probability probability density function. So it is calculated based on the ranges instead of discrete values.
Right.
So if we want to calculate for a particular range, we can integrate over for that particular range on the function.
Right. The last, Chintu, it's your turn now.
Random variable means the variable contains output of the random experiment or event. There are two types of random variables: discrete random variables, continuous random variables. Discrete random variables means defined output.
So we are now moving forward with expected value of a random variable. You all know what a random variable now is. So now you also know what a mean is, right? We have seen central tendency, we have seen mean and all that stuff in the last session. Now you are going to understand expected value. We call mean of a random variable as expected value. Expected value is nothing but mean of the random variable. Okay. So the expected value of a random variable is the measure of central tendency. You also know what is central tendency. What is the importance of central tendency? What this represents the average or mean value that the random variable would take in a long run. Okay. Average or mean value of the random variable that the random variable would take in a long run. Okay. So if it is a discrete case, what is the expected value of a mean? expected value of a mean. I mean, sorry, of a random variable. So E is nothing but expected value of a random variable, and it is calculated uh, with this formula sigma of x p of x. X starts from x is nothing but all the possible values of a random variable. You know what is discrete random variable, you know what is mean, and you also know what is the expected value now. Expected value is nothing but the mean of a random variable. So how are we calculating the mean of a discrete random variable? This is the formula. How to apply this formula? So if you take the dice, if you take the dice only, example of dice, can you apply this formula for the dice that we have just seen?
Yes, it would be summation of 1 to 6, with
Uh,
each value being 1 into 1 by 6, 2 into 1 by 6, 3 into 1
Right.
by 6.
So that's all. So x can take for rolling a dice, x can take all the values from 1 to 6. So x can take 1, 2, 3, 4, 5, 6. And now what is the probability of 1? Probability of 1 taking x as 1, it's 1 by 6 plus now x is 2. The probability of 2 taking value of the probability of 2 is again 1 by 6 plus 3 into 1 by 6 plus 4 into 1 by 6 plus 5 into 1 by 6 plus 6 into 1 by 6. So this is the expected value of, you know, of a discrete random variable when we are taking the example of it is. You remember this slide, right? So everything is taking a value of 1 by 6. So the probability of any random variable taking a specific value is 1 by 6. This is just we are applying. And then x can take, when you're rolling a dice, the x can be, the random variable can be 1, 2, 3, 4, 5, and 6, right? And now x is 1 into probability of 1 is 1 by 6. So if you calculate this, what you'll get? 1 by 6 plus 2 by 6 plus 3 by 6 plus 4 by 6 plus 5 by 6 plus 6 by 6. So what this becomes? 9, 10, 15,
21 by 6,
21 by 6. So what will the value of this?
3.5.
3.5. So this is the expected value of a random variable, the mean of a random variable. Okay, for continuous random variables, so the expected mean is calculated with this formula, integrating from within the range that we want to, and the x, I mean minus infinity to infinity, all the possible ranges. Like if the heights of students are extending from minus, I mean sorry, 3 to 6 feet, the integration will becomes 3 to 6. The integration will just become 3 to 6 x into the distribution, the probability density function of this heights of the students into d of x. Let's suppose the probability density function is given as x into dx. So this becomes x square dx. So the integration of x square will become x cube by 3. And we are applying 6 and 3 to this. And now if 6 is applied to this, 6 cube by 3 minus 3 cube by 3. The value of this will become the expected value of continuous random variable, which is the mean of that random variable. Got it?
Yeah, understood.
Okay. So you got this value now, right? 3.5. Does this make sense to you? Anyways, what this 3.5 represents, what is this saying? The expected value will give you a value. What is that value? The expected value of a random variable is the measure of central tendency representing the average or mean value that the random variable would take in long run. In long run, what is the mean value that the random variable would take? Is this 3.5 is making any sense to you? So what are the values that the random variable would take? It can take 1, 2, 3, 4, 5, 6, and the mean is coming as 3.5. Is that mean not falling here exactly in the middle of all the values that the random variable is taking in this case?
Yeah.
So this is central tendency, right? That is what mean actually is, right? We have seen mean, mode, median. They all are the central tendencies. And when you're coming to the random variable, the expected mean is the mean, the central tendency of the random variable. So random variable can take some set of values, and this expected mean will represent the mean, or the average of all those values, right? So what is the average of these values? 1 plus 2 plus 3 plus 4 plus 5 plus 6 by 6. Is it not the same?
Yes, it's
The same, right? So we have done the same calculation here. So both are same. So expected value is nothing but the mean. For the discrete case, this is the formula, and for the continuous case, this is the formula. In a long run, what is the value that the random variable would take is what the expected value will represent. It is basically the mean of a random variable, or the what is a random variable? Random variable is a variable that takes all the possible outcomes from that takes any of the possible outcomes of an experiment, right? So random variable, all the it takes on long run average or mean value that the random variable would take in long run is what the mean is. Understood? Any doubts here, or is that not clear to you? We are talking about expected value of a random variable. When you are talking about random variable, we will not say mean, we say expected value of a random variable. In long run, what is the value that the random variable can take? What is the highest possibility? Hello?
yes, it's clear.
Okay, let's take an example for the continuous random variable. So I'm taking, we have we've taken this example, right? 0, 1, 1. So now is equal to 1 is the equation of this. So so this is extending from 0 to 1, and f of x is 1 and dx. So x from 1 to 0. So this is 1. So in long run, what value it is going to take? It is 1. It is always 1, right? It is taking a 1 always from a uniform distribution function. So if it is normal distribution, what would be the mean of this normal distribution? What is the mean of this? I mean, I have the probability density function as this, which is normal distribution. We talked about normal distribution. What would be E of x for this normal distribution? If someone answered this, I can confidently say that he understood everything that we talked about till now. So you all know what is normal distribution, right? This is an example of normal distribution. And we also have seen this as a normal distribution, right? So for normal distributions, I think I haven't told you. Did I set this as mu, mean, and this is standard deviation, 2 times of standard deviation? Did I told you that?
No, no more, I think.
No, I haven't told you. But
Yeah.
I think we discussed it, right? So when we are taking the heights of students, um, the more common students will fall in this range, right? I mean, the average height of all the students will be in this range. Most of the students will fall around the mean. But when you go to the, I mean, tails of this curve, of this bell curve, you will get students with 3 feet height and 6 feet height, which is rare. Okay. I think this is not relevant if I don't explain you that. You cannot say what is the expected value of this. But for continuous cases, you understand this example, right? Uniform distribution, how to calculate the expected mean value of that continuous random variable. For discrete random variables, anyways, you understood this is 3.5, this is 3.5, this matched, and this is just representing the center value of the possible outcomes of random variable. For continuous random variable, this is the formula which says what is the value of the random variable in a long run. Okay, you got some understanding on this? Is this clear?
Yeah,
Hello?
yes, Mohan.
Okay. Okay. We are going to the next slide. And till this point, we understood what a mean is. Now we are going to calculate the variance of the random variable. What is variance means? You already have studied about variance. Variance is the spread of data points from the mean, right? Spread of the what is the dispersion of the data points around the mean is what variance is. The same applies to the same applies here as well. The variance measures the spread of variability of the random variables around its mean. So how far the values have spread from the mean is what variance measures. It gives an idea of how much the values of the random variables deviate from the expected value. Expected value is the mean, and variance says how far the values have distributed from the mean. And the formula for that is x minus e of x whole square into probability of x is equal to probability of each random variable. And you can calculate expected value of x and the x. And now tell me how do you calculate the value of variance of different data points? You have seen this, right? How do you calculate the variance of data points? Mean of the data points is sum of data points by number of data points, right? You have seen this calculating mean for, one
1
dimension. And what is the formula for variance?
1 by n summation xi minus mu whole square.
Very good. That is the formula for the variance, x minus mu whole square, where mu is what is the mu? Mu is the
Mean.
mean of the data points. We have seen all this stuff already. So we have seen variance. This is the formula I'm talking about. Okay. So we already calculated the variance of this. The same variance applies here as well for the random variables too. So this is the random variable calculation for discrete random variables and continuous random variables. What is the only thing that change between discrete and continuous? Discrete will be summation, continuous will be integration, because integration will give the area under the curve. For a continuous random variables, it would be a continuous graph, whereas for discrete variables, it would be a discrete graph. So for discrete, we do summation, and for continuous, we do integration to get the area under the curve. That is the variance of the random variables. Clear?
Yes, Anya.
Yeah. So I kindly request everyone to revise every session 1 or 2 times once we are done with this. Okay. Please understand there is a lot of effort behind this to make sure you understand. So I think you have to put the same kind of effort at least for few months to reach to that stage. So once you are there, only first few steps will be difficult, but once you understood the basics, the other stuff would be very interesting, and no one has to actually tell you to see this stuff and that stuff. You'll automatically go ahead and see that, or try to understand that. But first few days would be difficult, but try to revisit the videos again and again, and try to bring up the examples. And we have got very good tools right now, right? So we got ChatGPT, we got this Microsoft Edge, which will gives very good explanation of every stuff that you don't understand. Just type what you have and what you didn't understood, and you will get a clear explanation of that. So these are all very simple. But these are the basics to get an understanding of the rest of the stuff we are going to go through. So shortly, I think in next few weeks, in next 2 weeks, I would say, we will understand different machine learning models and the derivations, or the derivations of those models and how the models are working. We will do a complete understanding of that. At that point of time, you will use all these things. You have to understand what is variance mean, calculating the probability density functions and all that stuff. So please revisit everything that you're doing, that we are going through, at least for few days. From then it would be very easy for you. And we already discussed about this population and sample in the previous slide, right? Population means the entire set of individuals or items that you're interested in studying. So let's suppose authors in a particular state, studying gathering the information from every author. Every voter here would be the population. But if you are taking sample out of it, few person or few voters out of all the voters in a particular state is a sample. Okay. Population is the entire set of individuals or items that you're interested in studying. Sample is a subset of the population that is selected for the actual study. All the students in a school, a group of 100 students selected from the school. That is the difference between population and the sample. So when you calculate the parameters, the population parameters, when you calculate the mean and variance from the population, that is the ideal value. That is what you want to see. When you want to calculate the parameters from the sample, they are called as estimation sample of they are parameters of estimated population, estimated parameters. We call them as estimated parameters. We call mean and variance calculated from the population as parameters. Okay, mean and variance calculated from the sample is called as estimated parameters. So we are estimating population using the sample parameters. That's the reason we call as estimated parameters. We are not using the entire population to calculate these things. We are just using some of them, a subset of the population. That's the reason we are calling them as estimated parameters. They are denoted by the bar on the population parameter symbols. Let's suppose if you are representing mu as the population parameter and sigma as the standard deviation of those parameters. So in general, you will just we'll add a bar on top of that. Okay. So basically population, the sample will be represented by ST, standard deviation, and this is represented by sigma. Let's come back to these symbols later. Anyways, we will use them in the derivations, but it's rare that it's really rare. I don't say rare. We never calculate the parameters from the population. We always calculate the parameters from the sample. We calculate the parameters from the sample, and then using those estimated parameters, we will try to understand the population always. We never calculate the population. There is no point when you know the population entirely. There is no point of doing the statistics or doing the analysis on the population. You have the right information with you. That is the ideal information, and you are trying to reach or estimate those ideal parameters with little effort. With little effort in the sense by taking a sample out of it. You are not going to every voter. Instead, you are going to some subset of voters and trying to understand how the trend of the election is. That's all about population and the sample. And now, going back to the cosine similarity. Right. What's your time now? 12:30. There is all on that. So I'll just close this with these two slides. I'll go back with covariance and rest of the stuff in the next session. So now let's understand cosine similarity between data points. This is very simple. And you know how to calculate the angle between two vectors, right? What is the formula to calculate the angle between two vectors?
Cos inverse of
Hmm.
A dot product of B by modulus of A into modulus of B.
Right. So cos theta, when you're giving two vectors, if you want to calculate the angle between two vectors, you will just do this a bar into b bar by mod a mod b. Theta is just the cos inverse of this. So cosine similarity, what this cosine similarity says is how similar two points are. Okay. So if you want me to take an example, I'll just take a simple example for you. So how this says how similar in terms of direction, but cosine similarity is basically what we use to predict how close those 2 points are. Okay. So let me just show you one simple thing where we use this cosine similarity to cluster some points. It's just a simple English word, right? So you know what a cluster is. But let me just show you this. We have something called as clustering. So look at this example. So you look at this. We clustered different points which are close to each other, right? So this is what clustering means. Basically, when we do cluster, let's suppose this is the sample space. In this sample space, we have n number of points. Everything is in black color initially. Now, once we have all of them, once we have all the data points, you want to group the similar data points. Let's suppose, to take a simple example, you can have, let me take this copy and go back there to explain you better. So this is clustering. Okay. So how do we achieve this clustering? One way of achieving this clustering is, oh, sorry. Okay. One way of achieving this clustering is by looking at the cosine similarity of the 2 points. So how do we cluster? Basically, when 2 points are similar, we cluster them together, right? If you take the example of animals in a space, why two different animals be close to each other? Because the properties will be similar. What is the properties? There's the properties would be similar for those 2 points, or for those two animals. If you take a sample space of all the animals, in this we have dogs, 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 we have cats, 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 we have lines somewhere like this. So these are the features. I mean, based on the features, they might slightly differ, but they all fall at the same place. So that's the reason you can cluster them. So you can, when you are given n number of data points, you can cluster the animals based on the properties. These are, I mean, the attributes of this is different. The attributes of this is different. I mean, I can say this is tail length, and this axis is tail length, and this axis is strength. Okay, based on those two properties, I actually marked, I have taken these properties of different animals and plotted as a graph. So you can also give numbers to this: 2, 4, 6, 8, 9, 10, something like this. And this is 1, 2, 3, 4. So this dog strength is 2 and the tail length is 4. This dog strength is 2.5 and tail length is 3. That is what points basically means. How do we cluster those points? By taking the cosine similarity between 2 points. Okay, how similar they are. So when the cosine similarity for two orthogonal vectors is 0, cosine similarity of parallel vectors is 1. Okay, look at these two statements. I'm coming back again. Cosine similarity is a measure that calculates the cosine of the angle between two vectors, which indicates how similar they are in direction. How similar they are in direction, regardless of the magnitude. It doesn't consider magnitude. How similar they are in terms of direction. Cosine similarity of orthogonal vectors is 0 because cos 90 is, what is the value of cos 90?
0.
0.
Right. So what is cos 0?
1.
So
1.
when two vectors are more similar, the similar cosine similarity of 1 says the two vectors are similar. Cosine similarity of 0 says they are not similar. Okay, cosine similarity, when the angle between two vectors is 90, you can say they are not similar. When the angle between two two vectors is 1. When you say angle between two vectors is, cosine similarity is 1, they are similar. That's what it says. As the angle between the vectors decreases, similarity increases, right? So if you look at this, the table below over here, how is that actually increasing? When you come from 90 to 0, the value of this cos theta is increasing, right? The value of cos theta is increasing when you move from 90 to 0. So when the angle between two vectors is decreasing, so this is 90, right? When you say 90, they are not similar at all. When the angle is decreasing, both the vectors are getting similar. Vector is nothing but a point. Point is nothing but dog or cat or lion, whatever it is. When the angle between these 2 points are decreasing, they are similar points. Okay, you can use this as one of the parameters to do the clustering as well. Clustering means marking all the similar points at similar stage. Now you understood that, right? You got some basic understanding of what cosine similarity is and where it will be used. Got that or not?
Yeah.
Yes.
Yeah.
Now let's just take a simple example and determine this cosine similarity, or try to calculate the cosine similarity for those two, for those 3 or 2 points. You will understand when I take 3 points. Let me just quickly take an example so that you will better understand which are similar and which is not similar. Okay. Let me take 3 points now. 3 points would be A's and let me take 3 points now, and this is my origin, and this is A's. 10 years A's, and I have 80 years A's. And the calcium levels in their body is what I'm trying to calculate. Okay. So the calcium levels of 10 years A's is, I would say, 40. And the calcium levels of a person with 80 years is, I would say, 20. And I'll take another person whose calcium level is 79 with calcium levels as 22. Okay. Now I have 3 points now. A child with 10 years of age, an old person with 79 years of age, and another person with 80 years of age. Now I have 3 points, right? One is 10, 40 is one of my point. Agreed. 79, 22 is another point. And 80, 20 is my another point. Now you have to determine which 2 points are similar. Which are similar out of these 3 points. You have to find out which 2 points are similar. You anyways, by looking at this diagram, these two people are similar, right? 79 and 80 are similar, and 10 comes into different zone. He's a child, they are old persons, right? By looking at that, can you determine that? Are you able to determine that?
Yeah.
Yes.
Now calculate the cosine similarity. The theta. Everything is a vector. This is a vector, and this point is a vector, and this point is also vector. Now calculate the angle between these two, and say whether they are similar or not. If the angle is less, just look at these vectors by looking. Just not you don't really need to calculate, but just look at these vectors. By looking at these vectors, you can say the angle between these two vectors is same, but the angle from this vector is large. So can we use this theta to measure as a measure of similarity? If the theta is less, the 2 points are same. If you take 79.5, he might have somewhere here, which is much closer. If you are taking some 40 years of age, his calcium levels falls over here. It would be little farther from this. So can we now can you use cosine similarity to determine the similarity of 2 points based on that angle calculation? Yes or no? You can also do this stuff. You can just calculate the angles between these three and see the numerical values as well. If it is this still confusing with the diagram, I can just do that. What are points? We just have to find out the angle between find angle between. What are the 3 points? 3
10,
points
10,
is
40.
40, 10, 40,
29, 22.
79, 22, and the other one is
80,
80,
20.
20.
80, 20. Um, find angle between each of these points. So let's see what the angle says. So you want to find out the angle between 10, 40, 79, 22, 10, 40, 18 to 80, 20. And also you want to find out the angle between 79 to 18, 20. And then you will understand which two vectors has the minimum angle and which two vectors has the farther angle. So when the angle between them increases, cos theta will reach to 0. So that oh sorry, calculated in a different way. Between 10 and 79, 20.
No. Angle between each pair of points, you can say. No?
Yeah, try that. So by looking at these angles, 1040 has 60.40 degrees, 10 to 40, 18, 61.93, but 7922 has just 1.53. What does this mean? This means these two are this point is far from 7922, but these two are closer. The angle between them is just 1.53. So these two are similar points. So you can cluster these two and you can just leave this aside. I can introduce another point which is close to 1040. Okay. What I'll do is I'll just say 20, age is 20 and his calcium level is 34. Okay. So now let's look at the angle between the similar points. So by just looking at this example, you say 79, 22, 80, 22 are close to each other and that angle is less. So they can be clustered together, or you can say they are similar points. Now 10 to these two has 16.43 degrees. Okay. They are not so similar, but when compared to 17 and 80, they are little similar, right? So when you compare 20 to 72 and these are for 43 degrees. Between these two, they are 43 degrees. These two, they are more similar because the angle is very less. That's the reason they are very similar. These are similar, but not that similar as compared to 79 and 82. And the rest all are very far to each other. That is how cosine angle can be used, or cos theta can be used to find out the similarity between the points. Make sense now? And have you understand what is cosine similarity and how it measures the similarity between 2 points?
Yeah,
Yes,
yes.
ma'am.
Okay. So now it is just you are all very familiar between about this Euclidean distance. Euclidean distance between means that what is the straight line distance between two vectors? How can we calculate that? Is what this Euclidean distance basically is. Like if I have 2 points, this is 1 point and this is 1 point, and let me take 3 dimensions: x1, x2, x3 is one of these points, and this is y1, y2, y3 is this point. If I want, these are two vectors. right? If I want to calculate the straight line distance between these 2 points, it can be calculated as y1 minus x1 whole square plus y2 minus x2 whole square plus y3 minus x3 whole square. You already have seen this. This is Euclidean distance. I mean, this is just Euclidean distance that we calculate. Distance between any 2 points is just, in this case, it is just represented as a vector. Vector is again a point in that n dimension space. So when the dimensions exceed that we just have to increase the square content. That's all. That is what basically Euclidean distance is. Subtract and then square and then sum and do the summation. That is what the Euclidean distance basically means is. With that, we are done with this slide as well. Now I'll just end up here. I don't know what's the time there, but I'll just close with this covariance. Correlation is a different concept that we can anyways understand that later. This is all mean. You already know all this stuff. Mean vector or centroid in 2D. In one-dimensional space, what you will do, you will just do sum of the points by the number of points, right? That's what you do to calculate the mean in 1 dimension. But in 2 dimensions, what you will do, you will have to find out a point that is ux and uy. So in 2 dimensions, how does the points look like? In 2 dimensions, how do you look at the points? The points looks like this, right? So this is how the points look like in 3D. In 2D. So these are my points. So this is my x-axis and this is my y-axis. Every point will be represented as x comma y, which is, let's suppose this is 4 comma 2. And if I have to represent the mean of these points, how does that point looks like? How does that point looks like? It looks similar to this, right? It looks similar to this. So this is the mean of all these points, which is the center of all these points. So I have to calculate this. How does this look like? This looks like somewhere like mu x comma mu y, right? As it is a 2-dimensional space, every point has to be indicated with x and y. So this would be the mean of all these points. These are all the points in 2D space, and the center point of all of that would be the mean. So to calculate this mean, what you will do, you will just sum the let's suppose, let me just take 4 points. The 4 points like somewhere like this. So the points would be 1 comma 2, 1 comma 4, 2 comma 2, and 2 comma 4. To calculate the mean, what you will do, you will sum all the x values 1 plus 1 plus 2 plus 2 by number of points, which is 4. Right? That is what this formula says. Sum all the x components in your 2 dimension and then by n, which is 2 plus 2, 4, 5, 6, 6 by 4 is the x component of the mean vector. And what is the y component of it? It is just like 2 plus 4 plus 2 plus 4 by 4, 8, 10, 12 by 4. So this would be the mean. 6 by 4 comma 12 by 4 is the mean vector. It can also represented by the vector something like this. This would be also vector, as it can be represented by 6 by 4 I cap plus 12 by 4 j cap. This is x component, this is j component, unit vectors in that direction. That is how you calculate the mean vector. Clear?
Yeah.
Okay. Do you want me to stop or do you want me to close this covariance? And this is, I'm saying, this is as important as the probability density function. So you are going to understand covariance, correlation, and then you will understand this positive semi-different matrix. So covariance matrix as well. Those are the few basics that we are left with, but these are very important to understand. If a concentration is high, I can just go complete this covariance. And as this is the base for the rest of the stuff like correlation and all. If not, we can continue in the next session. It's your call now.
We can continue in next session now because it's already around 1. So
Okay. Then I'll just stop here. We can start from the next session.